our last class we have seen the structure of stack, and we have taken seen the corresponding statements like push and pop. So, today before going further we will explain the stack structure a bit more and with some examples, and then go towards the subroutine and calls and returns. So, as we said that in 8085 or for that processor, in any other processor or any other processor, the stack happens to be a part of the memory. So, if this is your memory, then this stack is a part of the memory which is declared, which is the stack, and then this stack can grow in this stack can grow in one direction. Normally it grows in the upward direction, though it is not mandatory that it will always grow in the upward direction, but in general it is made to grow in that way. So, conceptually we can view that stack as if a data structure like this, where at the beginning we are at the bottom of the stack, and that is pointed to by one special register, which is the stack pointer in case of 8085. Similarly, in other processors there may be some other name, but this is called stack pointer in 8085. So, at the beginning of the program, if a program is expected to use this stack, like say use the push and pop instructions, subroutine calls, etc., then the user is expected to initialize this stack pointer to some proper value. Otherwise, this stack pointer will contain some garbage value, this register will contain some garbage value, and this push pop they will start updating memory at some arbitrary locations. And if there is a possibility that with the stack pointer not being initialized properly, it modifies some essential part of the program or the essential part of the operating system. So, that way we should initialize this stack pointer. So, the way we should initialize the stack pointer is by the LXI instruction, LXI SP comma some value. So, in our last class we have seen that we initialize it to FFFF hex. So, that it means that it is the highest possible address at which the 8085 can have, and it is initialized to that. So, it is initialized to the bottom of the memory. So, but this FFFF hex, so this is not mandatory. So, you can if you find that your program in your system you can define the stack to be the maximum address is say 4000, then you can initialize the value to 4000, but that way you are absolutely free to initialize this stack pointer value, but we have to make sure that it does not corrupt other part of the data and program in the memory. Now, once this stack pointer has been initialized, so you can use the push and pop instructions to save the content of some registers into the stack, or get the content of content of the stack onto some register. And this is a LIFO structure, last in first out structure. So, the push operation, so this will put some data element into the stack, and the pop operation will take it out. So, push and pop they both occur from the same end. So, when you push it, so it is pushed, it is copied on the topmost element in the stack, and when it is popped out, the topmost element is popped out. And as we said that this push and pop instructions they work on register pairs. So, you can have an instruction like say push B. So, this push B instruction, so this will modify the stack in this way. So, we can say suppose at present the stack is suppose at present my stack is like this. So, it is this is my memory, and the current stack pointer is pointing to this location. Okay. So, this location is say the address 1000. I am writing in decimal. So, assume that the value is 1000. So, then so when this push B instruction is executed, first the stack pointer will be decremented. So, it will come to this location, and the content of C register will be put here. The content of the C register will go there, and then stack pointer will be decremented further. So, stack pointer will get the value 998, and at 998 the B register content will be put. So, for this B is as a register pair, it consists of the registers B and C. So, the C goes to the this actually as per Intel convention, the higher order byte will go to the higher order address. So, this will be the B value will be coming here, this will be the B value, and this will be the B value, and this will be the C value. Let me draw a fresh diagram, like if this is the stack, then this push B. So, if previously the stack pointer was here, the B value will be coming here and the C value will be coming to the previous location. So, if this value is this is memory location 1000. So, this is 999 and this is 998. So, this since the lower order C is the lower order byte. So, it will go to the lower order address location 998, and B being the higher order byte. So, it will go to the higher order address, that is 999. So, this way the push instruction is executed, and the stack pointer value SP will new value will become 998. Similarly, the pop instruction will do just the reverse. So, if you are executing pop B in this configuration, then first the content of this location 998, which is pointed to by the stack pointer, will be taken to the C register. So, this value will go to the C register, stack pointer value will be incremented to 999, and then the content of this will come to the B register and the stack pointer value will be implemented to 1000, as if two topmost entries have been taken out from the stack. So, this way this push and pop instructions are executed, and we have got for B, C, D, E and H L we have got register pairs. Also, for the accumulator register, it is not paired. Accumulator A is a single register. So, what is done with this A, this P, the flag register is added. Okay, this flag register is added, and this whole thing is given the name PSW. So, processor status word or PSW. So, that includes the accumulator and the flag. So, the accumulator will be saved first, and then the PSW, then the flag register. So, that way the values will be pushed into the stack. So, next we will look into the subroutine structure, and in the subroutine structure, so what happens is that a part of the program which is required several times, like in the last class we were telling that in my I may have a program where the particular function, say the square root calculation function, is required several times in the program. So, instead of putting the code several times, repeating the code several times, so we can just take it, say we can write it only once. So, we write this square root routine here, and wherever we need this square root routine, we call it from those points. So, there is an instruction call by which you can call a subroutine, and that subroutine will be executed by calling it at that position. A typical example can be like this. Say we have got suppose we have got a program, we write a function or subroutine that finds the maximum of, say B and C registers, and puts the maximum, puts the value in A. Okay. So, if I want to write this particular program, so I can do it like this, say move A comma B, then compare with C. So, I have got the content of B register into A, and that is compared with C. So, if it happens that B is already larger, so if B is if this accumulator is smaller than C, that is C is larger, then the carry flag will be set. Okay. So, if there is no carry, jump on no carry to say some label L1, otherwise we know that the maximum is the B. Okay. So, jump on no carry, that is B is already larger than C. So, in that case nothing happens, otherwise if the carry is there, that means C is larger than B. So, in that case I should move the content of I should move the content of C register into A, move A comma C, and then here is my label L1, and here I return from the subroutine by means of a rate instruction. So, we call it this subroutine, let us give it a name. So, let the name be max, let the name be max. Now, this subroutine we can use it to find say maximum of two numbers, like say in the memory. So, suppose I want to compare the contents of memory location 2000 with 2001. Okay. We want to compare the contents of these two memory locations and store the larger one, the larger value I want to store in say 2002. Okay. So, this program we want to write. So, we can do it like this. First we do an LXI H comma 2000, move first value I get in B register, B comma M, then INX H, move C comma M, and then I call this subroutine. So, I can call this subroutine by the instruction call max, and we know that at the end of this call the A register will have the maximum value. So, now I can save the value in 2002. So, I can say another INX H, and then I can say move M comma A. So, by this I can save the larger of the two numbers into the location 2003. So, this way I can write down the subroutines. So, this part of the subroutine that I have written, so it can be placed anywhere in the program. So, ideally we put it at the bottom of the main program. So, this is the main program. So, at the bottom of that we put the subroutine, but it can be put anywhere. So, it can be at any say some before this or after this. So, it does not matter. Okay. So, with that we will go back and discuss on the subroutine and all. So, subroutine it is a group of instructions that will be used repeatedly at different locations in the program. So, rather than repeating the same statement same instructions several times, so they are put only once. So, in this way it will save in the space requirement. So, the total program size will be reduced. But what about the execution time? So, execution time will be more, because we will see shortly that whenever you are going to execute a subroutine, the return address has to be saved onto the stack, or when you are coming back from the subroutine, the return address has to be popped out from the stack. So, that way the execution time will increase, but the size of the program reduces, the readability of the program improves. So, in assembly language program, a subroutine may be anywhere in the program, but it is customary to put at the end of the main program. So, next we will have see some subroutines in 8085. So, there are two instructions that deal with subroutines in 8085. One is the call instruction. So, the call instruction will be used for calling a particular subroutine. So, redirect the program execution to that subroutine, and how will it happen? So, this the way it takes place is that the program counter value will be loaded with the address of this subroutine, and that way the next instruction to be executed will be from that particular address. So, this way execution will be happening in case of call. And this return instruction, so return instruction is used for returning from the subroutine. So, when the subroutine ends, at the subroutine will end with a return instruction or RET. So, getting this RET instruction, the processor will pop out from the stack the two topmost entries, and it will put those values into the PC low and PC high, those two locations, those two registers. So, PC will now have the return address. So, you can understand that it becomes a responsibility for the processor that when it is going to the call. So, before starting the subroutine, it should save the instruction, just it should save the address of the instruction just after the call. Okay, so that after the call instruction. So, in case of so that it can return to the appropriate address. So, next so the structure of this call instruction is like this: call followed by a 16-bit address. So, what it does is that the push the address of the instruction immediately following call onto the stack, and then the program counter value is loaded with 4000. So, it is like this, that say this is the call instruction. Okay, this is the call instruction, then and this is at say location 1000, and call instruction, you can understand the size of this call instruction is 3 byte. 1 byte will be going for the opcode call, the second byte will be 40, third byte will be 00. So, this is a 3 byte instruction. So, my next instruction is at location 1003. So, this is my next instruction. So, what the system will do is that it will store this value 1003 into the stack. So, it will put it will push this 10 and 03, these 2 bytes into the stack, which is the current program counter value, and then only the program counter will be loaded with this value 4000. So, that my return address is saved onto the stack, and now I am ready to start execution of this of the procedure of the subroutine that we are talking about. So, we can do that. So, next we will see like how this return instruction is executed. This return execution is like this. So, it will retrieve the content of the return address from the stack. So, in the previous example, the 1003 is in the top of the stack. So, when this procedure finishes, this 10 is put into the PC higher order 68 bits, and 03 will be put into the lower order 16 bits. So, that is the 2 topmost stack entries will be popped out, and they will be put into the program counter, so that your program execution resumes from location to 1003. So, this is the usage of this call and return instruction. Now, there are some cautions, like this call instruction places return address at the 2 memory locations immediately before where the stack pointer is pointing. So, this is the some time back I was telling that before starting the actual code of the program. So, we should save the we should set this stack pointer to some proper values. So, if that is not done and your program uses the call instruction, then it will be putting those return addresses into whichever location pointed to by the stack pointer, and unfortunately, if that points to some valid program statements, program bytes, so that will also get overwritten. So, that may create difficulty. On the other hand, this return instruction it will be taking out the content of 2 topmost memory locations. So, naturally, if in a subroutine, so if you are not careful enough and modify the stack pointer register inside the subroutine, so that may cause harm, because while returning from the subroutine, so whatever be the stack pointer value, the processor will access the top 2 most locations and put them onto the PC. So, if the stack pointer is not proper, then it may again get some the PC may get some garbage value, and your program, instead of returning to your desired location, so it may return to some arbitrary place. It may not be even in the same program, it may be some arbitrary place within the memory, so it returns there. So, we have to be careful while manipulating this stack pointer register inside procedures. So, we should normally we should not do this, but if it is absolutely necessary, so we should be taking enough care to ensure that the stack pointer value is restored before the return instruction. So, next thing that we do is a subroutine. How are we passing data, passing the value on which the subroutine will operate. Now, we have already seen one technique by which you can do this, like the example we have taken to get the maximum of the 2 values stored at 2000 and 2001. So, there we have used that B and C registers to hold those two values. So, those are actually passing the parameters to the subroutine. So, this way the first option for doing this is to pass the values pass data to subroutine by means of registers. So, data stored in one of the registers by calling the program, and the subroutine uses the value from that register. So, whatever data, so in that case we require two values to be passed. So, you use two registers. If you require on say a single value to be passed, so you can use one register that way. So, this before calling the subroutine, we should initialize that register with the proper value, and subroutine will use that register value. So, as a result it will get the correct content, and then later on it is when the program returns subroutine returns, then maybe we can have some return value. But that is true if the number of values that you want to pass are less. Like I want to say we have got some general purpose registers like B, C, D, H, L, and you can also say that okay, I will also use the A register. So, that is total 7 bytes. So, if your data that you want to pass is restricted to 7 bytes, so the CPU registers may be sufficient. But if you are asking for larger size data to be passed, for example, you want to write a program, a subroutine that sorts numbers, and you want to sort say 100 numbers. So, 100 numbers cannot be passed through registers. So, there we have to pass through some memory locations. Okay. So, we can earmark some memory locations that will contain the input array. So, maybe we can fix some location, like we can say that the location, the memory location 1000 onwards, the 100 integers will be stored which are to be sorted. So, that way the subroutine will know that my parameters are from location 1000. Other possibility is that the agreement may be like this, that the HL pair. So, this will point to the memory locations that will contain the data, that will call from where the data will start. So, in that case, before calling the subroutine, I should initialize the HL pair with the proper value. So, that when I am in the subroutine, so I use the HL pair to index through the array elements. So, there can be two types of modifications that can occur in the parameters that we have passed. Okay. So, in one case, like in the normal case, like if you are say I have passed the parameters through the registers B and C, and inside the program it is just modifying those values. Okay. So, it is modifying the contents of B and C registers. Then once you return to the program, you do not get the original values of B and C, but you get the modified values of B and C. So, this may or may not be desirable. Sometimes we want that the modification carried out by the subroutine is really the modification that we desire. So, and in another case, so we may just say that okay, this value I passed just for as an input value, I do not want the register to get modified. So, that way these parameters, so that can be classified into two classes. One is called call by reference, other is called call by value. So, in case of call by reference, the values are modified in the subroutine. So, those register contents are modified, and as a result we do not get back the original values. Now, if you say that okay, I do not want to destroy the contents of those original registers, I just want to use it and do some calculations around that, but the result should not modify those registers. Then for doing it, we need to save the original registers using push instructions before using them in the subroutine, and we have to before exiting the subroutine, we should pop them. So, we will take a simple example, say like this. So, this is the subroutine, and we want that in this subroutine. So, this uses the registers B and C, and we expect that these values should not be modified, this register content should not be modified. So, this in the body of this subroutine, it modifies this B and C. Okay. So, it works with this B and C registers. So, that way it gets modified, but we do not want that these modifications will get reflected into the B and C values of the original of the calling program or the main program. Okay. So, how to do this is that in that case at the beginning of this at the beginning of the subroutine, we have to save the contents of those two registers. So, if this is the the first statement in this case should be a push B, so that the BC pair will be saved onto the stack, and after that I should have the code, whatever code is there, that will be there. Then at the end, before the return instruction, I should have the pop. So, this pop B, so it will restore the content of those B and C registers from the stack. So, the original values were saved in the stack at the beginning, original values are restored from the stack at the end. After that, I should have the return instruction. So, this way I should do, so that I can get I can get the implementation of this call by value. So, original values are restored before execution returns to the calling program. So, this is required. Then another interesting thing that we should have is that push and pop should be used in the opposite order. So, if you push at the beginning, if you have first pushed the register B, then push the register D, then the pop should be in the other order. It should be pop D first and then pop B first, then the pop B. So, because it is otherwise what will happen is that the values that you get are not correct. So, maybe at the beginning I have pushed in the order B and D, while popping, if I pop out B first and not D, then I will get the wrong value. So, if you have pushed like say if you have pushed like say push at the beginning, you have written like push B, push D, then at the end you should do like pop D first and then you should do pop B. If you change the order, then what will happen is that you will get wrong values, because first B has been pushed. So, in a LIFO structure, so first the value B has been pushed and then the value D has been pushed. So, while popping out, I should pop out this D value first and then the B value. So, if we change the order here, the D here, B here and D here, then I will get the original content of D register into B register and original content of B register into D register.